Hello, this is Scott. I'll be giving a short overview for QUCSstudio. It's for Quite Universal Circuit Simulator. I'll be using USIMIX version 5.8/5.9. What we'll be going over is the implementation of a stepped impedance filter. Then we'll show the layout tool, a stub, and optimizing a stub for a specific capacitance at a specific frequency, and then the use of the SNP block to ultimately create a matching network or show that a matching network works. Yeah, all the calculations and legwork was done off video. So this is really just a tutorial on how to implement your design in QUCS. Okay, let's get into it. First thing we need to do is open a new project named stepped filter. Because ultimately I want to implement a microstrip and a ideal transmission line version, we're going to need a couple of blocks here. First, we'll go to components, transmission lines. This is where we'll find the substrate block. Go ahead and name that FR4 as a relativity 4.2 and loss tangent and resistivity. This is the resistivity of copper, so we go ahead and leave that. Secondary, we're going to need a simulation block for S parameters. It's under components and simulations. Place that. We're going to start at 0.1 gigahertz and stop at 3.2 because that's the range of our DNA in the lab. And we're going to take 311 points because that gives us a nice step of 10 megahertz. Okay. Additionally, we're going to use a insert equation block here. Leave it like that. You'll see why in a second. Now, for the ideal transmission lines, we got to go to components. Under transmission lines, we got it right here. Boom. This is going to be a 6th order filter. So we need 6 segments of transmission line. In ADS, you usually have 3 parameters. That'll be your impedance, your frequency, and your electrical length in degrees. QUCS does a little differently. We just have our impedance and our length. So for ideal transmission lines, the speed of propagation here is going to be the speed of light. So that's what the equation block is for. We're going to be able to actually implement a vector that uses degrees to define our transmission line lengths. So let's go ahead and get that started. So for our low impedance line, we're going to use A impedance line. We're going to get a couple more here. So we need our frequency and our speed of propagation, which is the speed of light. So times 10 to 8. And we have a vector. These are going to be our electrical lengths in degrees for transmission line 1 to transmission line 6. Good, so we got 6 lengths here. Now we need to put in our equation for the physical length. It's going to be T over 360. Whoops. Perfect. Now, for the microstrip implementation, we're going to add our two widths, which are associated with high and low. Let's go ahead and actually just do our high and low impedances. So this is going to be 0.025202 meters. And for the high impedance line, 0.735 millimeters. Okay. So yeah, the default units are going to be in meters here. That's why we have those extra zeros. Cool. So now we need our ports. It's going to be under sources and AC power source. Okay. So I'm going to place two of those. And then I also need a ground. Unlike in ADS, term G blocks have the ground already incorporated. We need to place them ourselves here. So go ahead and connect it all up. So we start off with the low impedance. And this is going to be the first element of our length vector, like so. We can implement each length. Nice. So at this stage, we're ready to simulate. Let's pray that it works. Save this. Beautiful. Okay. Now to add a marker, top of the screen, the toolbar, we can place our markers. Okay. There's no way to actually type in the frequency of the marker. So we kind of have to drag it. That's why we chose for a step of 10 megahertz, so we could actually find our 1.8 gigahertz mark. Beautiful. So it looks like it's working roughly. We're near 3 dB for the cutoff frequency that we wanted. Next, we would like to implement our microstrip version. Go ahead and select microstrip line here. Do the same as before, place 6. Go ahead and copy this. Oh my goodness. All right. There we go. Now, because we're dealing with microstrip lines here, speed of propagation is no longer c, some other number. Hopefully we all knew that. So our lengths are going to be a bit different. Make sure this is in millimeters. Okay. 5.25. 15. 3.4. 0.02. And because in the real world, it's not like the filter is gonna start and end directly at the ports. We're gonna go ahead and add some extra lengths. To simulate what it might actually be like when it's fabricated. All right, I like it. What is this? I don't want that. Boom. Come on. Come on, Betty. There you go. Okay. On OCD, I'm just going to ignore it. That's fine. So for 50 ohms, 50 ohm line, this is going to be 3.06 millimeters roughly. All right. And then for the low impedance lines, we got WL, high impedance, WH. Okay. Whoops. That's looking good. All right, we're gonna go ahead and copy these, I think. Place. We'll run it. Come here. You could find the ports, the S parameters we're looking for in this column. Let's delete these. So we need collection coefficient in dB scale and transmission coefficient in dB scale. Go ahead and apply. Perfect. Deleted our markers, sadly, but that's okay. Boom, boom. See where we're at here. Yeah, that's one thing I wish they would fix. Come on, there we go. Yeesh. Boom. Okay. So there's our microstrip implementation. It's working great. S11 or S33 rather in this case of minus 3 dB. Collection or transmission coefficient, a little bit more attenuation. That's because of those extra added lengths, MS7 and MS8. So looks like everything's working properly. Okay, another useful feature of USIMX is to actually generate a layout. To do this, go to File, Export, and export in the ITE-CAD format. We're going to save. I already tested this, so I have to replace it just to make sure it's working, because in version 5.9, it does not work. There's a .dll file that is missing from the bin. That file exists in 5.8. If you're using 5.9, you can go ahead and copy that file and drag it over. Suppose we should. I can show you what that is actually. So yeah, it's this file right here, qt open gl4.dll. You're just gonna drag it over into your USIMX 5.9. Okay. All right. After you get the .ite file, gonna go to PCB layer outer. ite.e.cad, I think is an Italian, has the Italian colors. Okay, so we can go ahead and go to open project, select the file, open, go to board, and there you have it, the layout. And from here you can go to output and get the Gerber files and use it, you know, whatever other software you'd like KiCad or otherwise. Okay. One of the useful things in QUCS is the ability to plot Z parameters. Only way to do this, as far as I know, is to use the equation block here, where we transform our reflection coefficient into a complex impedance. Okay, so we have a stub here. This should give us a capacitance of around 10 picofarads at 1.2 gigahertz. So let's go ahead and simulate. As usual, gives us S parameters here automatically, but we want our impedance, or really our imaginary part of the impedance, transformed into a capacitance. So let's go ahead and do that. So it's 2 times pi times frequency times the imaginary part of Zn. Graph. Let's delete this one. Apply. Now it's hard to read. We're expecting minus 12. We're expecting 10 picofarads. So let's go ahead and do this. Apply. Let's go minus 11. Okay. Cool. So 10 picofarads should be about this line right here. It's good. Put down a marker. We're almost there. 1.2. So we're looking at like 12 picofarads. Well, there is an optimizer tool, so we can find the ideal length of our stub with this optimizer. Okay, so to use the optimizer, we're going to need to define a goal. So let's go ahead and do that. We need admittance. Okay. This is going to calculate the capacitance here. So y on 1 2 times 5 times. Wait. Let's see. Okay, and then we're going to go see target. We want, what is it? 1e minus 11. Okay. Cool. We also need to add an error. So we got, see target. Want the difference between the target capacitance and the actual. Apply. Now let's go to simulations. We have it open, optimization. Put it like it's up here. All right. So there are no variables, no goals. The way we set the variables, we right click on L, add to optimizer. It's added automatically. Termination tolerance. Let's make it. Guess that's fine. Initial step. 10 micron. No. All right, we know we're already pretty close. So we'll leave this as max what it is. Initial that. 27.5, something like that. Should be good. Okay. Now we need to set our goal. We got our error here. Goal here is we want to minimize the error, right? So we go the optimization block, error, minimize, perfect. go ahead and run this. Okay. So on the right, we have our goal capacitance, number 1. Let's go ahead and see what it actually is. That would be useful, right? Okay, so we go to diagrams, tabular. Okay. This is actually the optimized value. So let's go ahead and apply this. It's okay. There we have it in meters. 28.5 millimeters. Okay. So we can actually just copy this, 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 and this. And we'll just open a new schematic, copy it in there. 28.5 millimeters. It's good. Run it. Do as we did before. Over 2 times 5 times. And looking good. Limits. Let's try that. Ah, yes. So that back to the way it was. Sorry about that. Okay, looking good. Let's place our marker. Nice. Okay. So there you have it. Much closer to 10 picofarads. So yeah, that's how you use the optimizer. All right, really quickly, just want to go over how to use the SNP block to import your measured S parameters from some element that you were testing in the real world. In this case, we'll be using electrically short monopole. These S parameters or SNP file was gathered from a VNA at the lab. So here's our SNP block. This is how it spawns in. Comes with 2 ports. We want 1. And then we have some test file. Well, we have our SNP file here and under project_prj. This is where you'll put yours. Go ahead and select it, hit open, apply, okay. Let's connect it up. So this setup is how you would, or how you can measure the input impedance of your SNP block directly. So let's go ahead and simulate. Now, to get the Z parameters, as always, we're going to get the complex impedance here. We use the equation block. Okay. Oops. And we're going to tabulate it, normalize it by a characteristic impedance. I suppose, oh, one thing, make sure that your notation's in real and imaginary. There you go. One thing, I guess we could just that. Yeah. All right, so we're interested in matching at 1.2 gigahertz. So you would come in here, find 1.2. There you go. You got your normalized input impedance for your load. Put that in on your Smith chart, and you can design your matching network. So yeah, we have the matching network here, as usual, for a single open circuited stub. Come some length away from the load and jut out some length and terminate with a open circuit. So here it is. Blue is showing our matched load, and red is showing our unmatched load. Okay. Thank you very much, you guys. I enjoyed making this tutorial for you. You'll have a good one.